Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. This is for aerospace engineering. Yesterday, during our Google Meet, I started working through a truss calculation problem. And I'm going to try to work through the problem now completely from beginning to end. So, a truss is a triangular shape. And this is a simple one that I've drawn here. And I've chosen to draw it on graph paper. It's convenient, and there's a trick you can use when you have a truss structure drawn on graph paper. And as I work through this, that should become apparent to you how that's going to be helpful. But to describe it, a truss is a massless rod. It can only pull or push in the direction that it's drawn. So it can't pull or push to the side. And I have here a simple truss, one triangle. I've labeled the left vertex A, the top one B, the right one C. This triangle that I drew underneath vertex A is the symbol that represents that it's pinned at that point. That means it can rotate, the structure can rotate about point A, but it can't translate, it can't slide left or right, and it can't go up or down as well. It's pinned in place. Underneath vertex C, I've drawn the symbol for a roller, a circle. And that means, like it sounds like, that it's sitting on a wheel, that it's not pinned, it's free to slide left and right. Mm. So, what I've done is I just made up this problem and I said, suppose I have a 100 Newton force being applied horizontally to the right at vertex B up here. The first step you would have to do in a truss structure is to draw the reaction forces. So those are all the forces that are on the outside of this truss acting on it as a single structure. Later on, you will be asked to analyze the compression and the tension for each one of these members. But first things first, you have to do the reaction forces. So there's three guiding statements about the reaction forces. The sum of all the forces in the horizontal direction have to add up to zero. The sum of all the forces in the vertical direction also have to add up to zero. And the sum of all the moments, or as I call it, the torques, about any arbitrary axis also have to add up to zero. So because I chose to do this on graph paper, I've laid out a coordinate system with the origin at vertex A, so its coordinates are 0, 0. Vertex B is 9 squares to the right and 5 squares up, so its coordinates are 9, comma 5. And vertex C is 12 units to the right and 0 units up, so its coordinates are 12, comma 0. Those are the coordinates that I jotted down. Now, applying these rules to this structure to come up with the reaction forces, I've just redrawn the triangle only with the vertices shown right now, maybe trying to make it a little clear to you how I come up with the reaction forces. So there's a load being applied to the right at point B that has a magnitude of 100 newtons. I can't cancel that at point C because if I pull on C, it's actually going to roll to the right. It's free to move horizontally left and right. So it's not going to be resisting any kind of force applied to it there. The only place where I can cancel this 100 Newton force to the right is at point A. And so therefore, at point A, there has to be a reaction force to the left in the amount of 100 newtons. So there it goes. 100 newtons is the reaction force at A in the horizontal direction, and it's going to the left. You might label that as reaction force A horizontal direction equals negative 100 newtons as far as notation goes. But wait, there's more. Even though you don't see any vertical forces being drawn here, there are vertical forces here. And they come about in order to keep this thing from rotating about point A. So if I take this protractor and pretend that it is the truss structure for a moment, and if it's free to rotate, when I apply a force off to the right, it's going to tend to make this thing want to rotate about point A. And so I have to account for that. That is a torque calculation or a moment calculation. Torque or moment is the product of the distance from the axis of rotation to the point of application of the force times the magnitude of the force times the sine of the angle between those two directions. Now, in this situation, you could pull out some trig and say, okay, this is at coordinate 9 comma 5, and therefore the inverse tangent of 5 over 9 gives us the angle that it makes above the horizontal. That will be the angle that it makes relative to the force up here. You could do that, but here's a trick you can use, and it's one of the nice tricks when you do this on graph paper, is you are allowed to slide the force along its line of action. The line of action is a dashed line that points in the direction of that force, and it extends behind it, and it also extends in front of it. So here I've crudely drawn a dashed line, which you can't really see too well. But the point mathematically is I can slide this force forward or backward along that line, and it doesn't change the moment or the torque caused by that force. So what I'm going to choose to do is to back that force up along its line of action until it is directly above point A. And I'm going to draw it here, pointing to the right, and label it as 100 newtons. That's not a different force from this one because a force isn't a starting point. A force is a magnitude and a direction, not a starting point. So this 100 Newton force is this 100 Newton force here now that I've backed it up to that point. So there aren't 200 Newtons going on here. I've relocated this 100 Newton force to be directly above point A. The advantage of that is now I don't even need a calculator because the direction from point A to the force that is directly overhead is straight up. Sorry you're having trouble seeing the contrast here. I suppose I could try darkening it. Straight up. And that is my 0-degree direction for doing a moment calculation. It's measured from the axis of rotation to the point of application of the force. So this pen right now is pointing straight up. The direction of the force is to the right, it's horizontal. And so the angle between the pen and the pencil is negative 90 degrees. Because we're always working in the math circle, when we're going clockwise, it's a negative angle. When we're going counterclockwise, it's a positive angle. The sine of negative 90 degrees is negative 1. So very conveniently, the twisting force, the torque caused by this 100 Newton force being applied at point B is 5 times 100 times negative 1. The torque is negative 500 Newton meters. I'm going to presume that every square here is a unit of 1 meter and that my force is in units of newtons, and therefore my torque is negative 500 Newton meters. Excellent. Well, that will cause this whole truss to rotate about point A. It has to be counter-torqued someplace. And I can't counter-torque it at A because the distance from the axis of rotation to A is 0. That would make R 0. And 0 times any force is still 0. So I can't apply a twisting force through point A that has anything other than 0 value. The only place left is way out here at point C. Point C is 12 units off to the right from point A. And I can't apply a force in a horizontal direction at C. It would just roll on that roller. So the only direction in which I can apply a force at point C is vertically. And I need to apply a positive torque at point C to counter the negative torque being applied at point B. A positive torque means the direction from A to C, taken to 0 degrees, to the direction of the applied force has to be a positive direction, going counterclockwise, like on the math circle. So the force at point C, and I'm going to draw it down here, must be an upward force. So I just drew this arrow here. This is point C. So here I haven't drawn the triangle, I've merely drawn the three vertices. And I can calculate its force. So I'm going to label it reaction force at C in the y direction. It must counter the torque caused by the 100 newtons being applied at point B. Therefore, given that the distance from A to C is 12 meters, given that it has to have a total torque of positive 500 Newton meters, I would say 500 Newton meters divided by 12 meters must be the magnitude of the reaction force at point C. So 500 divided by 12, and it's not a convenient number, but oh well. I get 41.7 newtons. In fact, I'm just going to round it off, and I'm going to call it 42 newtons today. Maybe I shouldn't, but I'm going to. All right, so that reaction force is pushing up at point C. If I go back to my full triangle, so there's really a force pushing up at C. There's really a force pulling A to the left from the wall that it's attached to or from the pedestal that it's mounted on. And we still have to respect the sum of all the forces adding up to 0. So in the horizontal direction, 100 newtons to the right is canceled by pulling A 100 newtons to the left. In the torque, the torque caused by 100 newtons at B twisting around point A is canceled by the 42 newtons at point C going up vertically. Those two torques cancel. But I still have vertical forces to cancel out. Now that I've created a vertical force where the roller is pushing upwards at point C, there has to be a counter force in the vertical direction to cancel out those 42 newtons up. It can't be at B. It can only take place at A. And so maybe this doesn't seem too logical to you, but at point A, this pin has to be pulling down on point A with a magnitude of 42 newtons. So I'll just draw that, I suppose, down in this diagram. Doesn't really matter which one I'm choosing to write it on, but reaction force at A in the y direction is negative 42 newtons. Not the scale, but I'm trying to show that there's an arrow pointing down at point A. This is the reaction forces acting on the original truss. So we started with these massless 3 rods, the dimensions given, the load given, and from that, we've determined that there is a reaction force at A in a magnitude of 100 newtons, another reaction force at A downward with a magnitude of 42 newtons, and a reaction force at C with a magnitude of 42 newtons. This is the first and necessary step to doing truss analysis. You cannot go inside the truss until you have the correct reaction forces drawn acting from outside the truss. So the roller's outside pushing up, the pin here is outside, it's pulling down, it's pulling to the left, and the load is outside, pushing B to the right, or pulling B to the right. Having had completed drawing the reaction forces, now we can go inside the truss and calculate the compression or the tension for each one of these members. Just like this pen, each one of these members is either being pulled apart or pushed together. Pulled apart or pushed together. That's all they can do. And a, a complete truss analysis is to calculate how much force is being applied to each one of these three members. So this is the part we did not get to yesterday during the Google Meet. Of course, it's fun to do, and I'm now going to try to do it in real time for you. So I'm going to begin my analysis at point C, because in my mind, I can see what I need to do there. So I want to remind you that at point C, there is a force going upward, and I'm going to say it's 42 newtons. And at point C, this is point C, is not allowed to move. That means the sum of all the forces acting on point C have to add up to zero. All we've said so far is that the roller underneath point C must be pushing upward with a force of 42 newtons. Somehow, something must be canceling those 42 newtons. Now go back to the original truss structure. Point C has a roller pushing up on it, and it has two truss rods connected to it. A rod can only push or pull in the direction that it's drawn. So this horizontal rod that connects point A to point C can do absolutely nothing about the 42 newtons that's being exerted on point C upwards in the vertical direction. There's only one rod that can do anything to counter it, and that's rod BC. BC connects point B to point C, and it can either push or it can pull. Now, in this situation, it has a job to do, and that job is to cancel out the 42 newtons being exerted on point C by the roller. So the only way it can do that is if it is pushing down with a magnitude of 42 newtons. So I've just drawn it. Here's this little sketch. This must be coming from rod BC. Now, if I were to do this to scale, what you would see, let's see, this is 3 squares by 5 squares. So if I count 3, 1, 2, 3, 4, 5, and 5. So B to C is this rod on the graph paper. I'm drawing just the rod. Here's point B, here's point C. The roller is pushing up on point C with 42 newtons. And now rod BC must be pushing down on point C with a magnitude of 42 newtons. But that is the vertical component of a force that must be exerted in the direction of this diagonal line. And so what I'm creating is a right triangle. This right triangle has one leg of length 5, one leg of length 3. Sorry, you didn't see that. One leg of length 5, one leg of length 3, and in terms not of physical distance, but in terms of magnitudes of forces, the magnitude of this vertical force must be 42 newtons. Okay, not 5 meters, but 42 newtons. Now, by similar triangles, the ratio of this leg to that leg to the hypotenuse is the same as the ratio of the components of the forces acting on through truss BC. So if this vertical leg is 5 units and this horizontal leg is 3 units, then if this horizontal leg is 42 newtons, then if this vertical leg is 42 newtons, then this horizontal leg must be 3/5 of 42 newtons. And rather than do that in my head, I'm going to just use my calculator and then round it. So it says 25.2, but I'm going to call it 25 newtons. That is the horizontal component of the force of truss BC acting on point C. This must be pushing down and to the right on point C. The vertical component must be 42 newtons, and the horizontal component must be 25 newtons. And so you can now calculate by Pythagorean's theorem the diagonal. And I know I rounded off a little bit as we went, but that's what I'm going to do just to get this done quickly. Rounding off, well, it says 48.9. I'm going to round that off and call it 49 newtons is the magnitude of the force acting between B and C. Now, the last thing I would do is to show. So if B is pushing on C, so I have the pencil here, right? The eraser is point B and the pencil tip is point C, and B is pushing on C. Well, by Newton's third law, C must be pushing back on B. For every action force, there's an equal and opposite reaction force. So the pencil, my question for you, is it being compressed between B and C, or is it being pulled apart? Am I pulling the pencil apart, or am I squeezing the pencil together? If I'm pulling it apart, that's called tension. If I'm squeezing it together, that's called compression. In this situation, B is pushing down on C. I suppose I could go like this, right? B is pushing down on C. C is pushing back up on B, and the pencil is being compressed. So we would normally label this with a letter C, and I myself tend to draw it with arrows pointing from the inside of this truss to the vertices at the two ends of it. So I just added an arrowhead here, an arrowhead there, letter C for compression. So this guy is being squeezed. And I'm choosing to represent that with these outward facing arrows. If he was being pulled apart, I would reverse the arrows, and that sounds a little backwards, doesn't it? Oh well. Good thing I have the letter C, because even if the arrows don't quite make sense, it's certainly a true statement that this rod is being compressed between B and C. All right, that's one of three rods. Now we have to go on and do the other two. The order in which I would choose to do this one is actually I would do AC next, is what's coming to my mind. Looking at point C, I realize that I have two forces acting on it caused by rod BC, a horizontal force and a vertical force. The horizontal force has a magnitude of 25 newtons. Rod B is pushing, rod BC is pushing point C to the right with an applied force of 25 newtons. It would roll, so there must be some force other than the roller that is keeping point C from actually being moved to the right. Rod AC is the only one that can do that. So rod AC must be pulling point C to the left in the amount of 25 newtons. So A is pulling C, and by Newton's third law, for every action, there's an equal opposite reaction. Point C is pulling point A, pulling towards each other. It's like a tug of rope, and one person on each end is pulling on the rope. So A is pulling C towards A, just as C is pulling A towards C. Newton's third law. So the reaction force at point, I shouldn't call it the reaction force. The horizontal force at point C has to have a magnitude of 25 newtons pulling C to the left along rod AC. And that means, of course, that at point A, if I were to draw just point A by itself, here's point, here's point A by itself, it must have 25 newtons pulling it to the right, caused by C. So, I've established what the tension is between A and C. It's a pulling force. If I represent with the pencil, it could be represented with a rope instead of a bar. I can't represent BC with a rope because you're pushing it, squeezing it together, it would just collapse. But I can use a rope between A and C because it's under tension. So T for tension, and the magnitude of this tension is 25 newtons. All right, so we still have to do rod AB. We still have to figure that one out. And I see I didn't quite draw this where I should have. I should have drawn point A there as far as this diagram goes. All right, now, you're not done until you do all the truss members. And we still have truss member B to take care of. Here's some logic that goes with point B. It's not allowed to move. All the forces acting on point B have to add up to zero. All the horizontal forces, all the vertical forces. What's going on so far is that rod BC is pushing on point B just as much as rod BC is pushing on point C. So to make a point of it, if I were to draw just point B by itself, I know that for starters, it is being pushed to the left in the amount of 25 newtons by rod BC. And it's being pushed upwards in the amount of 42 newtons, also by rod BC. And that is a consequence of Newton's third law. So if B is pushing down and to the right on C, then C is pushing up and to the left on point B. Up in the amount of 42 newtons, to the left in the amount of 25 newtons. Now, point B is not allowed to actually move. The sum of all the forces have to add up to zero. There's only one truss structure that can stop point B from moving, and that is truss AB. So truss AB must be pushing B to the right and simultaneously pulling it down to cancel the stuff all out. So yowzers, right? At point B, AB must be pushing to the right and at the same time pulling it down. So that doesn't quite seem to make sense. All right, I'm going to have to pause and think about this for a moment. Think. Probably made a sign error. Hmm. It seems wrong. The advantage of doing this is I could stop it and then I could just, I paused it and figured out what I was overlooking. So back on point B here, I was overlooking the fact that there's a load being applied, pushing it to the right in the amount of 100 newtons. Rod AB has to also overcome that 100 Newton load force, not just the two reaction forces from rod BC. So there's really three pushes and pulls going on at rod B that has to be compensated by rod AB acting on it. And so here was what I kind of overlooked. At point B, rod BC is pushing up on it in the amount of 42 newtons. Rod BC is pushing to the left in the amount of 25 newtons. And so what I had drawn was I said, well, so rod A has to be pulling down with 42 newtons and pushing B to the right in the amount of 25 newtons. So what did I forget? I forgot that there is a 100 Newton force, the load, acting on point B. And so to keep B from moving, rod AB should not be pushing B to the right with 25 newtons. Instead, it should be pulling B to the left. Now, rod BC is already pushing point B to the left in the amount of 25 newtons. The load is pushing rod point B to the right with 100 newtons. So what's left is that rod AB has to pull B to the left, the difference of this amount, which is immediately 75 newtons. So here are the two correct numbers. Rod AB has to, this is A, this is B. Rod AB has to pull point B to the left by 75 newtons and pull down on it in the amount of 42 newtons. They form the two legs of the right triangle connecting point A to point B. So if I now type in 75 squared plus 42 squared, take the square root, I see that I get, call it 86 newtons, is the magnitude of the force of rod A acting on rod B. And what is it doing? Meaning, final decision. Is it compression or is it tension? So A acting on B. If this eraser is point B and the pencil tip is point A is pulling point B down and to the left. So conversely, B is pulling A up and to the right. So if they're pulling on this pencil, can I represent this pencil with a solid rod or can I replace it with a rope? If I can replace it with a rope, that means that this rod is under tension. It's being pulled apart. If the forces cause it to crumple up, then I can't use a rope for that. I have to use a rigid structure. So A is pulling B, B is pulling A, and you should conclude that you could use a rope in this situation, that it's a tug of war, and that this particular truss element is under tension. All right. Whew, that was close. Ciao.